Good morning all. In today's lecture, let us discuss about nucleus. Its general property, its stability, the NZ graph which explains about the stability of the nucleus. Right? So now here, one day, Rutherford, he was doing experiment on gold foil. He incident alpha particles on this gold foil. Right? Now, when he incident alpha particles on gold foil, he observed that some particles without deviation are passing through the gold foil. Some particles, alpha particles, undergoes lesser deviation, and some alpha particles, in which way they went, they bounced back in the same way, in the same path. They bounced back in same path. And he did experiments on this, why alpha particles are behaving in such a way. His experiment led to the conclusion that all the positive charges present in the atom accumulate at one particular point or concentrate at one particular point, that is at a central portion of atom, and he named that region as nucleus. So his experiment said that all the positive charges in the atom concentrate at one particular point, that is central portion of atom, that he named as nucleus. So in such a way Rutherford discovered nucleus, and around this nucleus electrons revolve in a circular path. And he even gave the explanation why these rays are going undeviated. So according to his theory, there will be a lot of empty space between this nucleus and electron. So only some of the alpha particles went without a deviation. So in such a way, nucleus was discovered by Rutherford. Now the question is, who discovered the proton? The question is, who discovered the proton? So actually, before Rutherford, William Prout. So three scientists are there who talked about these positive particles. Today we call it as proton. First scientist who talked about these positive particles is William Prout. According to William Prout, all the atoms consist of hydrogen atoms itself only. Means positive particle means he named it as hydrogen. For him, positive particle means hydrogen. Hydrogen 1H1, you know. So according to him, all atoms consist of hydrogen atom. Now the second thing is, Goldstein, when he was doing the experiments, he found that one kind of rays, a glow, is passing from anode towards the cathode. So he named these rays as canal rays, and he said that these rays are positively charged. So only they are moving towards the negative cathode. Okay, he named these rays as canal rays, and these are positively charged. Now, but after this theories only, Rutherford, he discovered nucleus. After the discovery of nucleus, the total credit went to the Rutherford only. So now, who discovered the proton means, we will say Rutherford discovered the protons. Why means, even though these both talked about the positive particles or positive rays, but after the discovery of these nucleus, the total credit went for Rutherford itself only. So only we say Rutherford discovered the proton. Do you know who discovered electron? J.J. Thomson discovered electron. Who discovered neutron? Chadwick discovered neutron. Chadwick discovered neutron. Right. Now, according to Rutherford's theory, nucleus means what? So, nucleus means it consists of protons. And after discovery of Chadwick, it came to know that even in nucleus, along protons, a chargeless particles called as neutrons also lie in the protons. So protons are positively charged, right? Neutrons are chargeless. So the charge on nucleus is only due to the protons. As neutrons are chargeless, the charge on the nucleus is only due to these positively charged protons. Right? When protons are in the nucleus, then 100% there must be repulsion between the protons, no? Here no other charge is present. Neutron is not giving or providing any charge. Only protons are providing the charge to the nucleus. Means nucleus is completely filled with positively charged particles along with chargeless neutrons. When these are present, then there must be repulsion between the protons, no? When there is repulsion between the protons, nucleus must break. But is it happening? Nucleus is not breaking. Instead that, what is happening? The protons and neutrons are binding each other. They are binded to each other. Then what is binding this proton and neutron? How the nucleus is getting stability? Now let us discuss this. What are that which are binding the neutron and proton? Right? So before going to that theory which binds the neutron and proton, let us go for the general theory first about stability. Okay? So after discovery of a neutron by Chadwick, Heisenberg, he proposed proton-neutron theory. He proposed proton-neutron theory. Heisenberg, he proposed proton-neutron theory. According to his theory as usual, the nucleus consists of protons and neutrons. The number of protons we call it as atomic number. The proton plus neutron sum we call it as mass number. Alright. So now next, let us go for the stability. So now that nucleuses are stable in which number of neutrons is greater than protons. So that nucleuses will get stability in which number of neutrons will be greater than number of protons. Now if neutron to proton ratio is greater than 1, then these nuclei are stable. Okay? If neutron to proton ratio is greater than 1.5, these are heaviest nuclei, heaviest stable nuclei. Their atomic number is greater than 82. Their atomic number is greater than 82. Right? Now next, now the question is, as a number of protons is increasing, as number of protons is increasing, what happens? The repulsive force increases, right? When repulsive force increases, the nucleus must break. When repulsive force increases, the nucleus must break. But nucleus is breaking no. How it is happening? How it is happening means there are some kind of short range attractive forces. Okay? There are some kind of short range attractive forces, and these forces are strongest forces in nature. These forces are strongest forces in nature, and these forces exist between neutron proton in such a way, and these forces compensate the repulsive force. So only nuclear stability we are getting. These forces compensate the repulsive force between the protons. So only we are getting nuclear stability. In detail about these short range forces, let us go in our next topic. Before going for that, let us once know what are beta rays. So in my last lecture I said that beta rays means nothing but fast moving electrons coming out from the nucleus. Fast moving electrons coming from nucleus means whether electrons are present in nucleus. The question will arise whether the electron is present in nucleus. Then answer is electrons are not present in nucleus. Many experiments said that electrons are not present in nucleus. Then from where these beta rays are generated? These are nothing but the fast moving electrons coming out from the nucleus itself only we are saying. But electrons are not present in the nucleus. Then from where this electron formation is taking place from the nucleus, and how these beta rays are formed? Actually, the electrons does not exist in the nucleus. But before the emission of the beta rays, they are formed. Now, if this is a nucleus, now beta ray is going to eject from the nucleus. At that instant only these electrons will form. कभी का इलेक्ट्रॉन फॉर्म होके न्यूक्लियस में नहीं रहती. जब बीटा रेस they are going to eject from the nucleus, at that instant only electrons are formed in the nucleus. Then how these electrons are formed? That electrons only we are calling beta rays. Then how these electrons are formed? How these electrons are formed means they are produced due to the transformation of neutron into proton. When neutron transforms into proton, the electron is produced, and these electrons eject out from the nucleus in form of beta rays. Now you understood? In nucleus, the electrons will not exist inside the nucleus. Before the emission of these beta rays only, at that instant only electrons are produced. And how these electrons are produced? When neutron transforms into the proton N01, when transforms into proton H11, the electrons are produced, and these electrons eject from the nucleus in form of beta rays. Okay. Now not only these electrons, but even the positron emission, the electron carrying positive charge, we call it as positron. So positron means nothing but electron carrying positive charge. We call it as positron. Even positron emission is also possible. And how the positron emission takes place means when this proton converts into the neutron or transfers into the neutron, we get a positron. Okay. So now from this what we are understanding, see here. Neutron is transforming into proton, proton is transforming into neutron. Neutron is transforming or converting into proton, proton is converting into neutron. So we can say that proton and neutron are mutually convertible. Proton and neutron are mutually convertible, we can say. And we can also say that they are two alternative states of single heavy nuclear particle. They are nothing but two alternative states of single heavy nuclear particle. We call it as nucleons. Right? Now, I said that electrons does not exist in the nucleus. Before the emission of beta rays, at that instant when beta rays are going to emit, at that instant only the electrons are produced and comes out in form of beta rays, I said. Now let us go for the experimental proof. So that experimental proof that electrons never exist in the nucleus, that is impossibility of electron being in nucleus as a consequence of uncertainty principle. The uncertainty, based on uncertainty principle, let us see whether the electron can stay in nucleus or not. So according to uncertainty principle, the uncertainty in momentum of electron is written as delta P greater than or equal to h cut by delta x, where h cut is equal to h by 2 pi, where h we call it as Planck's constant. Now substituting these values, we get delta P value as 1.1 into 10 to the power of minus 20 kg meter per second. Right? Now next, if T represents the kinetic energy of electron, the electron having the momentum 1.1 into 10 to the power of minus 20 kg meter per second has kinetic energy greater than its rest energy. Now kinetic energy means mc square, no, m naught c square. Now c is velocity of light 3 into 10 to the power of 8 meters per second. M naught the rest mass. Okay. Now next, writing this as m naught c into c. M naught c is nothing but what? Momentum. So momentum value we got as 1.1 into 10 to the power of minus 20 and light velocity is 3 into 10 to the power of 8. So now the value of this T value in million electron volt we will get as 20.63 million electron volt. Right? We will get 20.63 million electron volt. Now, for a moment if we think that electron is present inside the nucleus, then kinetic energy of electron must be greater than 20.63 million electron volt. For a moment, let us think that electron is present inside the nucleus. If it happens, then the kinetic energy of electron must be greater than 20.63 million electron volts. But electrons emitted during the beta decay does not possess large amounts of kinetic energy. Their energy will vary from 2 to 3 million electron volt. Their energy varies from 2 to 3 million electron volt. But if electron want to exist in nucleus means its kinetic energy must be greater than 20.63 million electron volt. But the electrons coming out in form of beta rays will have the energy only between 2 to 3 million electron volt. So from this it is confirmed that it is impossible for the electron to stay inside the nucleus. Right? It is impossible for an electron to stay in the nucleus because electron need the energy more than 20.63 million electron volt, but here the electrons coming out from the nucleus is having only the energy from 2 to 3 million electron volt. So it cannot exist in the nucleus. right? Now next, nuclear forces. Now before what I said, the repulsive force between proton and proton is balanced or compensated by short range attractive forces, I said. And that short range attractive forces, we call it as nuclear forces. We call it as the short range attractive forces, which are the strongest forces in the nature, which are compensating the repulsive force between the proton and proton in the nucleus. We call it as nuclear forces. So nuclear forces is nothing but the force of attraction between proton-proton, neutron-neutron inside the nucleus. Okay, proton-neutron inside the nucleus. And the nature of these nuclear forces is they are strongly attractive forces which overcome electrostatic force of repulsion between the two protons. These are the strongest forces in the nature which are overcoming the electrostatic force of repulsion between the two protons. Alright? There are three types of nuclear forces. One is proton-proton force, the force between two protons. Proton-neutron force, the force between proton-neutron. Neutron-neutron force, the force between neutron-neutron. Alright? So now the properties, these are short range forces, these are charge independent, these are strongest forces in nature, these have saturation property. Saturation property means each nucleon interacts with only limited number of nucleons nearby it. Each nucleon interacts with only limited number of nucleons nearby it. Because nuclear forces are limited in range. The reason for that is nuclear forces are limited in range. They are identical for all nucleons and at a distance less than 0.7 Fermi, these force becomes repulsive. These force become repulsive. Now next, let us go for nuclear properties. The first property, nuclear mass. So mass of nucleus means sum of neutrons plus protons. They are expressed in atomic mass unit. One atomic mass unit equal to 1.66 into 10 to the power of minus 27 kg. Mass of nucleus, it is written as ZMP plus NMN, where Z atomic number, MP mass of protons, N number of neutrons, Mn mass of neutrons. And this mass of nucleus will be less than real mass. Now let us discuss in details about these in our next video in semi-empirical mass formula. Now next, here just let us go for properties itself only. Now the next one is, experimentally it is found that the real nuclear mass will be less than ZMP plus NMN. Next, nuclear charge. The charge on nucleus is only due to the protons. So total charge on nucleus means how many protons are there? That only gives the total charge, that is Z into E. Okay, Z the number of protons, E the charge of each proton. The charge of proton. Right. Now next, nuclear radius. To find the nuclear diameter, Rutherford did the experiments in two ways we can find it. Okay. One is by scattering of fast neutrons or protons, by scattering of high energy electrons. Alright. Now by doing this, they founded the radius as r equal to r0 a to the power of 1 by 3, where r0 we call it as linear constant, and the value of that is 1.4 into 10 to the power of minus 15 meters. A we call it as mass number of nucleus. Now the next property is nuclear density. So density means nothing but mass by volume. The same formula here we are using. Mass number into mass of proton by volume is 4 by 3 pi r cube. Substituting the r value from the above equation, r naught a to the power of 1 by 3, and taking r as 1.5 into 10 to the power of minus 15, we will get 1.67 into 10 to the power of minus 27, a by 4 by 3 pi 1.5 into 10 to the power of minus 15 whole cube a. And the density value will be 1.18 into 10 to the power of 17 kg per meter cube. Right. Next, nuclear spin. Nucleus also have spin like electron and proton. So that spin we call spin angular momentum, that is equal to half h by 2 pi. Now due to the spin of nucleus, due to spin, the nucleus possess magnetic moment. Next, even the nucleus also have the set of quantum states, and the transition between the different nuclear states are accompanied by the emission of gamma rays. Okay. Now let us go for stability of nucleus. Right. So Yukawa-Meson theory gives the answer for what is binding the proton and neutron. I said that protons and neutrons are binded in the nucleus. Right. Then what is that particular particle or energy which is binding the proton with a neutron? Because proton is having charge, neutron is not at all having the charge. Then what is that particular energy or a particle which is binding this proton and neutron? The answer is given by Yukawa. So Yukawa said that in nucleus, in 1935 he said, in nucleus not only proton and neutrons stay, but there is some other type of field between these nucleons. That field he named as meson field. So these mesons bind nucleons. These mesons bind nucleons. So according to Yukawa theory, nuclear forces arises due to the continuous exchange of positive and negative particles between the nucleons. So what I said, there will be a short range attractive forces between these nucleons, I said. How these short range attractive forces are produced in the nucleons? The question will arise. I said there are nuclear forces, that is short range attractive forces between these nucleons. That forces are only binding this proton and neutron. I said no. So here not only proton and neutron but mesons will exist in the nucleons. So here what is happening? How these nuclear forces are arised? Due to continuous exchange of positive, that is proton, and negative particles, that is meson. So nuclear forces arises due to continuous exchange of positive and negative particles between the nucleons. Now these particles are known as mesons. They named it as mesons because their mass lies between electron and proton. Their mass lies between electron and proton. Okay. Now the exchange of meson between two nucleons develop an attractive force between them. How the attractive forces are developed? Due to the exchange of meson between the two nucleons, the attractive forces are developed. Now let us see. Mesons may have two charges. Positive charge, we call it as pi meson, we write it as pi plus, or negative charge pi minus. Okay, and also we will have uncharged pi zero meson. This is uncharged pi zero meson. Mesons are supposed to exchange rapidly between nucleus by changing their identity. What I am saying? they are exchanging rapidly between the nucleus by changing their identity. How it is happened? Let us see. Now this is only bounding the proton and neutron together. They are changing their identity rapidly. They are exchanging between the nucleons rapidly by changing their identity, and this only bounding the proton and neutron together. How? Let us see. First, now when pi plus meson jumps from proton to neutron, proton converts into neutron. It is jumping from proton, no? So what we will write? P minus pi plus. It is converted into neutron. Neutron again takes pi plus meson, converts into proton. In such a way, a force of attraction between neutron and proton is formed or not? So, the nuclear force between neutron and proton is formed. See, P minus pi plus gives neutron. N plus pi plus gives proton. Means a nuclear force between neutron and proton, Np, is formed. Similarly, let us see. When pi minus meson jumps from neutron to proton, what happens? N minus pi minus gives proton. P plus pi minus gives neutron. Means here N is converting into proton, P is converting into neutron. So a nuclear force exists between P and a nuclear force exists between P and N. So P is binded with N. Here N is binded with P. So due to the exchange of these meson, pi plus meson, what is happening? N is binded with P. That force we call nuclear force. And due to the exchange of pi minus meson, what is happening? P binded with N. P binded with N. In such a way, proton neutron binds. Then you may ask, what about PP? Here pi 0 meson exchanges. Okay. So pi 0 meson exchanges. So in such a way, proton and neutron or neutron and proton are binded with each other due to the exchange of mesons rapidly between the nucleons. I think you are clear. What is binding proton and neutron? The rapid exchange of mesons between the nucleus are binding the proton and neutron. While this rapid exchange only, the nuclear forces are created. The nuclear forces are created which binds this neutron proton, proton neutron. Right? So in such a way, the nuclear attractive forces exist between PP, NP, Pn. Right? So these forces are large enough to overcome the electrostatic force of repulsion between the protons. In such a way, the stability of nucleons will be, so nucleus will get the stability. In such a way, nucleus will get stability as the repulsive force is overcome by these nuclear forces. Right? Now the next question is, right, will meson have any mass? Yes. Meson will have finite rest mass. When meson have finite rest mass, then that mass must be added to either proton or neutron, no? When meson is having finite rest mass, that mass must be added either to proton or neutron, no? But we are not finding any increase or decrease of mass in the nucleons. Then what is the reason? Why this mass is not added to the proton or neutron? Actually, here what is happening means, mesons are constantly running between nucleons. Okay, mesons are constantly running between nucleons. Okay, so neutron to proton, proton to neutron, in such a way they are constantly running between the nucleons, means constantly they are emitting and absorbing. These nucleons are constantly emitting and absorbing the mesons. You so know p minus pi plus. So p minus pi plus, here emission converts into n plus pi plus, here absorption. So constantly the protons, that is the nucleons, are absorbing and emitting the mesons. So according to Heisenberg uncertainty principle, it is impossible to detect any change in mass of nucleus, because continuously emission and absorption of mesons are taking place. Either if only emission takes place, then we can see the change in or detect the change in the mass of nucleons, or if continuously absorption of the mesons takes place also, we can detect the changes in mass of nucleus. But here both are happening continuously. Simultaneously the emitting and absorption is taking place. Simultaneously the emission and absorption of the mesons are taking place. So uncertainty principle says that when simultaneously emission and absorption takes place, it is impossible to detect any changes taking place in the mass of the nucleus. Right? So this is about Yukawa mesons theory. Right? Now next, let us go for NZ graph. Okay? So NZ graph is drawn by taking neutrons on y-axis, proton number on z-axis. NZ graph is drawn by taking number of protons on x-axis, number of neutrons on y-axis. Now you see the graph. Now let us go for point wise, one after other. So up to 20, right? Up to 20. This is a straight line. Graph is a straight line. Okay? So now here, for atomic number less than 20, for atomic number less than 20, this is n, this is z, no? N equal to z. Up to here, how the graph is? Graph is a straight line, right? It says that light nuclei are more stable. The nuclei, light nuclei means whose atomic number is less than 20 or up to 20, are more stable. Now see, from here the curve is departing. Actually in such a way the curve has to pass. The straight line has to pass in such a way. But instead of that, what is happening? The curve is departing. It is moving towards the neutron axis, I can say, no? It is moving towards the neutron axis. So as we go in upward direction, it is moving or bending towards the neutron axis. Right? Now let us see what is happening this. Now this blue color dots you are seeing, no? This we call it as beta minus particles, particle emitters. This red color dots we call it as beta plus particle emitters. Now here the curve is bending for atomic number greater than 20, and at the same time number of neutrons also will be greater than 20. And here the stability curve, how it is bending? It is bending along n greater than z. Okay, as z increases, that is number of protons increases, the curve departs more and more from stability line. Okay, if this is the stability line, it is departing more and more from the stability line. Hence, heavy nuclei are more stable. What I said? For stability, number of neutrons must be greater than number of protons, I said. Now here, as the atomic number is increasing, the curve is bending or departing more and more towards this n neutron axis itself only, which says that number of neutrons are more here. So the heavier nucleus have more stability. Okay. So now here I indicated about beta minus and beta plus. No. In these terms, let us explain about the stability of a heavier nucleus. In these terms, let us explain about the stability of the heavy nucleus. So now here, beta minus, three regions we are getting in the curve: beta minus, beta plus, alpha particle emitters we didn't show in the curve. It will be on the top of the curve. So beta minus means unstable nuclei above the stability curve. Unstable nuclei above the stability curve, these blue dots. Unstable nuclei above the stability curve, and beta plus are unstable heavy nucleus below the stability curve. Unstable nuclei below the stability curve. So now here, beta minus means they are rich in neutrons. So we call it as neutron rich particles. So now these unstable nuclei must gain stability. They must gain stability means what must happen? They must lose the neutrons here. Means here neutrons are more. When neutrons are more, the nuclei become unstable. Okay. So now they have to lose the neutrons and gain the stability. Then how they will lose the neutrons? They lose the neutrons by beta decay process. By beta decay process. So in such a way, in beta decay process, they gain the neutrons, they gain the protons and lose the neutrons. They gain the protons and lose the neutrons and becomes stable. Now next, beta plus. Beta plus means they are poor in neutrons. They are having less number of neutrons. So only they are unstable. So two kind of heavy nucleus we are talking. Some nucleus are having number of neutrons more compared to the protons. So in order to gain the stability, they have to lose the neutrons. And some nucleus will have less neutrons. Proton number will be more. So in order to gain the stability, they have to gain the neutrons. So now this we call it as beta plus particle emitters. So here what happens? Now here they have to gain the neutrons. How they will gain the neutrons? By positron decay they will gain the neutrons. How they will gain the neutrons? By positron decay. So due to positron decay, what is happening? Atomic number is decreasing by 1 and neutron number is increasing by 1. Atomic number decreasing by 1 and neutron number increasing by 1. So in such a way, below 20 they are stable nucleus. As atomic number increases, the nucleus starts losing stability. Here some nucleuses are having neutrons in more number. Some unstable nucleus will have neutrons in more number. Through beta decay process, they loses the neutrons and gain the stability. And some nucleus are having less number of neutrons. Some unstable nucleus are having less number of neutrons. Now in order to gain the stability, they have to gain the neutrons, and that gaining of neutrons is done by positron decay. So in such a way, here the curve is departing towards the neutron axis, indicates that nucleuses are gaining stability. Okay, so below 20 it indicates that lighter nucleus are stable. Above 20 it indicates that heavier nucleuses are also stable. But how they will gain the stability? Either by losing or gaining the neutrons, they will gain the stability. And above 82. Now above 82 what is happening? 82 is lead. And above 82 from 83, the nucleus will be unstable. Here what is happening? Above 83, the nucleus is emitting alpha, beta, gamma radiations. Above 83 and mass number above 209. These nucleus will emit alpha, beta radiations and transfer into lighter ones. Already in my last lecture I explained uranium converts into thorium by alpha decay. Means the heavier nucleus is converting into lighter nucleus. No? The 92 uranium, thorium 90. Heavier nucleus converted into lighter nucleus by emission of alpha particle. Right or wrong? So in such a way, the nucleus whose atomic number is greater than 83, they will gain stability by emission of alpha beta particles. They convert themselves into the lighter ones and gain the stability. So in such a way, stable nucleus every time will have even number of protons, even number of neutrons. So the particular nucleus which is having even Z, even N are more stable nucleus. So in such a way, NZ through NZ graph, we are knowing about the stability of the nucleus. Up to 20, all the lighter nucleus are stable. Above 20, how the nucleuses are there? So above 83, we didn't showed in the graph, that is alpha particle emitters. Alpha particle emitters, we talk above 83. Now up to 83. Up to 83, how the nucleus will be? Some nucleus will be unstable. In that unstable nucleus, some nucleuses are having number of neutrons more compared to protons. So by losing the neutrons through beta decay, they gain stability. In some nucleuses, unstable nucleuses, what is happening? They are poor in neutrons. So by gaining the neutrons through positron decay, they will gain stability. Now if we talk about the alpha particle emitters, this is above 82, that is above 83, from 83. Now from 83, how the nucleus is gaining stability? By emission of alpha beta particles, they convert themselves into the lighter nucleus and gain the stability. In such a way, the nucleus will try to gain the stability. So if you like this lecture, like it, share it, subscribe it, and stay with my channel Reshma Physics. In my next video lecture, I will talk about semi-empirical mass formula, binding energy curve, binding energy, what is binding energy, mass defect, binding energy curve, liquid drop model, shell model, and what are magic numbers. Thank you.